What's up, everyone? I hope you guys are having a great day so far. It's Ben, and today we're going to be covering first order linear differential equations. I'm going to be covering a few examples and showing how to solve them step by step. First off, a first order linear differential equation comes in the form of y prime plus a function of x times y equals another function of x. And this is just the general form that you'll see it in. It's not too important, but it's just important to know so you can recognize a differential equation and know that, okay, this is a first order linear differential equation. Let's go ahead and apply this certain technique or this method. So, and the method I'll be showing to you today is called the Bernoulli method that I was taught in my class last semester, and I think it's a great technique. It's not too hard to follow, so let's get right into it. So the first example we'll be covering today is the differential equation y prime plus 3 over x times y equals x squared. And we do have an initial condition as well. We have y of 1 is equal to 1/2, which is, we'll handle that at the very, very end. So we can recognize that this is in the form of, y prime plus a function of x times y equals another function of x. So the first step of the Bernoulli method is to go ahead and set y equals to u times v. Now, we're going to take the derivative of both sides with respect to x, giving us y prime equal to, and now we have u times v, two functions being multiplied by each other, meaningly through the product rule. So now we have u prime times v plus u times v prime. Let me go ahead and move this a little bit to the side. So now this is helpful because we have a y in our equation, so we can substitute this u times v, and we also have a y prime. We can substitute this product rule over here. So substituting it in, we get u prime times v plus u times v prime plus 3 over x times y, which was our u times v, equals x squared. Now, the next step is, every single time we do this, or most of the time we do this, we're going to be able to factor out a u, right? We have a u right here. We also have a u right here, meaning we have a common term. We can go ahead and factor that u out, which results us in u prime times v plus u, and when we go ahead and do a parenthesis since we're factoring out a u, we get v prime plus 3 over x times v equaling x squared. Now, this next step is, it's going to be a little bit confusing for the first time saying this, but we're going to get this whole equation in here, this expression. We're going to go ahead and set this equal to 0. Okay? We're going to go ahead and set this equal to 0, and we're going to set it up as an equation. We're going to deal with it. So, we're going to work this on the side. We get v prime plus 3 over x times v equal to 0, right? We set it equal to 0. Now, we can recognize this as a separable differential equation, which is the most basic of differential equations that we know how to solve already. So we can go ahead and just just straight up solve this. So we have dv over dx, since that's what v prime is. We're going to move this to the other side, so subtract 3 over x times v. Now we can divide x by both sides. Right? And now get the dx on the other side. So we have 1 over v times dv equals, so we have this negative still, negative 3 over x dx, right? Now, integrating both sides, we get natural log of v equals negative 3 natural log of x. We're not going to add a plus c. Don't worry. No need to add plus c to this yet. We'll go ahead and deal with that later. So now we need to solve for v. But so our first thing that we would think of doing is raising both sides to e, or applying e to both sides. But before we do that, let's go ahead and apply a log property to make this a bit easier. What I mean by that is that, see, we have the form right here. We have this in the form of a times natural log of b. And remember, this is equal to natural log of b raised to the a, right? So knowing that, write that formula down if you don't have that down already. We can rewrite this as natural log of x to the negative 3. Okay, now we can go ahead and apply e to both sides, giving us v equaling, because these cancel out, we get x to the negative 3. And boom, we're halfway done, right? We now solve for v. So let's go ahead and split this because we're going to have to solve the rest of the equation now. Since we set this part equal to 0, this u goes away, right? U times 0 is 0. So what we're left with is u prime times v. All this is 0, equaling x squared, right? So we have this u prime times v equaling x squared, okay? But now we already know what v is, so this is much easier. So we can go ahead and plug in this v right here, giving us u prime times x, write that better, x to the negative 3 equals x squared. Now, this is another separable differential equation, which is very easy for us to do. So we're going to go ahead and multiply both sides by x cubed, because this right here will turn to just 1. And then now we have u prime equals x squared times x cubed, which is x to the 5th power, right? We just add the powers together. So remember, u prime is just du over dx, right? Now, very simple separable equation. We just have du equals x to the 5th times dx. Integrating both sides, we get u equaling 1 over 6 x to the 6th plus c. Now, whenever on this last step where we solve for u, we will be adding a plus c. Don't worry about adding plus c to the v part. Only add the plus c when you solve for u. So now we're basically done. We have v, we have u. And remember, in the very beginning, we set y equal to uv. So going back down here, we have y equals to u times v. Our u, we already found it, so let's go ahead and plug that in. 1 over 6 times x to the 6th plus c times x to the negative 3. Simplifying this, right? Foiling this in, we get 1 6. Remember, we add the powers, so we get x cubed. And then here we just get c over x cubed. And remember, any power that's negative just goes in the denominator, right? So this is what we have now. We're basically done. We just need to go ahead and solve for our c using our initial conditions, which is this, right? Remember, the 1 here means we plug in 1 for all the x's, all of our inputs, and our output will be 1/2. So that means we're going to set y as 1/2, and we're going to plug in 1 for all the x's. We have this 1 cubed plus c over 1 cubed. Simplifying this, we get 1/6 plus c, right? The ones just don't do anything. Subtracting 1/6 of the other side, we get 1/2 minus 1/6 equals c. Getting common denominator, right? 1/2 is also 3/6. 3/6 minus 1/6 is 2/6, which 2/6 is just 1/3. So for our c, we get 1/3. Now, plugging this c back in over here, we get y equals 1 over 6 x cubed plus 1 over 3 x cubed. Or just writing it in the most simple form we can, just 1 over 3x cubed. And that's it, our final answer. not too hard, especially if you've already taken all your calculus classes. These integrations and these derivatives shouldn't be too much of a challenge for you. If they are, I strongly recommend going back and taking more notes on just your basic derivative product rule, chain rule, all that stuff, and your integration techniques. Because especially in differential equations, it's very integration and derivative heavy. So having those down will really help you, speaking from experience. And so yeah, I hope that wasn't too complicated. We're gonna go over another example so this can be much more clear. On to the second example, we're gonna have a little bit of trig involved to test your trig techniques and trig skills, and hopefully I can teach you something new here. So we have the differential equation sine x times y prime plus sine squared x over cosine x times y equals 1. And so this is an example where we don't have a first order linear differential equation right off the bat, right? It's not in the form of y prime, right? The y prime needs to be isolated, right? It's usually in the form of y prime times a function of x times y equals a function of x, right? We don't have this, so let's go ahead and get this into this form. So to isolate y prime, we need to go ahead and times everything by 1 over sine x, right? Same thing as dividing by sine x. So rewriting, we get y prime plus, right, in this sine x and this sine squared x, one of them will cancel out, leaving us with sine x over cosine x, equaling 1 over sine x. Now we do have it in the form. We have it in this form, right? Which is perfect. Remember, sine x over cosine x is equal to tangent. So we have y prime plus tangent x equals, and I know you might be tempted to rewrite this as cosecant, because 1 over sine x is cosecant, but we're actually going to go ahead and just leave it like this for now. Now, we can go ahead and apply the Bernoulli's method, right? Like we did previously. We did y equals u times v. Derivative of both sides, we get u prime times v plus u times v prime. Substituting this into our equation, we get u prime times v plus u times v prime plus tangent y, right, times y here. So we have this tangent x times uv equals 1 over sine x. Sorry about that. Yes, there was a y there that I didn't write. There's supposed to be a y. That's why we have a uv here. Remember, like the last step, last example, we factored out a u from this second term and this third term, which now we will have y prime times v plus u parenthesis, right, we're factoring it out, v prime plus v times tangent x equaling to the same 1 over sine 1 over sine x. Now, remember, we set this whole thing equal to 0, and we worked on it on the side over here. So what we have is v prime plus v times tangent x equals 0, right? Making this, rewriting this into a separable differential equation. We're going to move this to this side. Now we're going to get divide equals minus tangent x dx. Antiderivative of both sides, we get natural log of v equals, and actually the antiderivative of tangent is actually natural log of secant, of secant x. We saw the negative out in front. Remember, don't add a plus c. Now, remember what I did last time. We have a constant on the outside. I'm going to go ahead and bring it in, right? And remember, let's remember our trig. So secant is actually 1 over cosine x. So applying a negative 1 power, it's actually going to bring that cosine x up and giving us cosine x, right? Now we have natural log of v equaling natural log of cosine. Okay, I hope that's not too confusing, right? So, remember, now we can apply e to both sides, giving us v equals cosine of x. Boom. First step done. Now, on to the other part of the equation that we have. We have u prime. Remember this part right here. This is all 0. So we have what we have remaining is u prime times v equaling 1 over sine x. Substituting in, I'm going to rewrite, go ahead already rewrite this as du dx. Substituting our v, we have cosine x equaling 1 over sine x. Not too bad, not too bad. Moving the cosine x over, we get du over dx equaling 1 over sine x times cosine x. So now we're gonna go ahead and do a little small trick. It's honestly really cool. It's really something that you won't really never really see when integrating. But what we're gonna go ahead and do is use the Pythagorean identity, which is, if you don't remember, is cosine squared x plus sine squared x is equal to 1, right? And we have a 1 right here. So we're going to go ahead and just rewrite this whole thing as sine squared x plus cosine squared x over the same denominator. I know it looks a little bit more confusing, but it's actually going to help us out a lot here. So we can go ahead and now, since we have a plus here in between, we can go ahead and separate it into two different fractions. Now that we did that, we can go ahead and cancel one of these sines and cancel out one of these cosines, leaving us with sine x over cosine x plus cosine x over sine of x. And now, I know this is getting pretty long, but this is a good example so you guys can be exposed to these harder, challenging problems. Sine x over cosine x, remember, is tangent. So we're going to go ahead and rewrite that as tangent x plus, and then cosine over sine, right? This is just the opposite of this, right? It's just a reciprocal, meaning we have cotangent of x. Remember, we can go ahead and bring this down over here. We still have this du over dx, but we can go ahead and move the dx over here. Now we can go ahead and integrate both sides, right? With a separable differential equation. We're still on the same thing. We're just doing some manipulation to get to a point where we can integrate. And now the antiderivative of this side is going to be u. And if you don't know exactly what the antiderivatives of tangent and cotangent are, well, I mean, the last one we just did of tangent was natural log of secant x plus, and the antiderivative of cotangent is actually natural log of sine x. And then here we are going to add a plus c. Remember, for our u, we always do add a plus c. But we can go ahead and just do a little bit more simplifying here to make it look easier. Remember, recall our natural log properties. We have natural log of a plus natural log of b is the same thing as natural log of a times b. That's what we have here, right? We have a natural log of something plus another natural log of another thing, meaning we can go ahead and just write this as natural log of secant, which remember secant is 1 over cosine times sine x plus c. And remember, sine x over cosine x, like we've already done it so many times already, is just natural log tangent x plus c. And that's our u. I hope I'm not going too fast for you guys. Make sure you leave in some comments down below if I'm going too fast, going too slow, or if it's just right. Please let me know. The feedback is greatly appreciated. Anyways, continuing, right? We have our v and we have our u, meaning, remember, y is equal to u times v. So going over here for our final solution, we have our u, which was natural log of tangent at x plus c times our v, which was just cosine x. Now, that's the final answer. We're going to go ahead and just make it look cleaner by just foiling this in, giving us cosine x times natural log of tangent x, and then plus just c times cosine x. And that right there is our final answer. Not too bad. Remember, it's the same technique that we were doing. We just did a little bit of more manipulation over here, right, to integrate this. There's other ways to integrate 1 over sine x, cosine x, but what we did here was just using the Pythagorean identity, where 1 is equal to sine squared of x plus cosine squared of x. And that helped us a lot here. It just simplified very nicely, and we just used the table integrals. Remember, if you don't really need to remember what the antiderivative of tangent and cotangent are. For most tests, you can bring a page of notes, or if you can't bring a page of notes, maybe you will have to remember it or learn how to derive the antiderivative. But other than that, not too bad of an example. And I want to do one more example for you guys. So for our last example here, we have the differential equation 2x minus y squared, all times by y prime, equaling the 2y. But it's very important to notice that this is not actually a linear differential equation, not in terms of y, because a linear differential equation is where we have y prime, and it's not being multiplied by a y, and the y's are to the power of 1. But here we clearly have a y squared. So this is not a first order linear differential equation. It's a first order nonlinear differential equation in terms of y. We don't know how to handle those yet. So we're going to actually do a bit of a trick, and we're going to handle this in terms of x's. So what we're going to do, it might be a little bit weird to look at first, but we're going to go ahead and multiply this whole equation by dx over dy. Because remember, this right here is dy over dx. So multiplying this dx over dy into everything will actually, these right here will cancel out, right? The dy's cancel out and the dx's cancel out. So what we're left with is 2x minus y squared equals 2y times dx over dy. Now we're going to do the same technique that we did last time, Bernoulli's method, but we're going to do it with x's instead of y. We're going to go ahead and we're going to do x equals uv instead of y equals uv. So let's go ahead and get it into the form that we know. So let's go ahead and isolate the dx over dy. So we need to divide everything here by 1 over 2y, giving us, I'm going to go ahead and write this with the dx dy on this side, because that's how we like to read it from left to right. So now we get, so dividing everything by 2y, this 2x just turns into x over y, and then here we have just y over 2. Now we have the dx dy isolated. Now we need to get a function of y on the right side by itself. So subtracting this x over y to the left side, we get dx over dy minus x over y equaling to negative y over 2. Now this is a first order linear differential equation with a function of x, right? We have it in the form of x prime plus a function of y times x equaling to a function of y, right? It's a little bit weird. We're working with x's instead. So knowing that, we're in a good spot. Now we can go ahead and apply the substitution, or the x equals u times v. Remember, same thing, product rule. Now, going ahead and plug this into our equation, we get u prime times v plus u times v prime minus x, sorry, not x, we have 1 over y times our x, which is u v equals negative y over 2. Remember, factoring out a u from both of them, we get u prime times v plus u parenthesis v prime minus 1 over y times v equaling to negative y over 2. Remember, setting this equal to 0, we can go ahead and work on this on the side. So we have dv over dy, sorry, dv over dy, and then minus 1 over y times v equals 0. Separable differential equation again, right? We like these because they're easy. So now, getting the v and the y's on different sides, we can go ahead and divide by v and multiply by dy. So we get 1 over v dv equals 1 over y dy. Integrating both sides, this is pretty routine by now. We get natural log of v equals natural log of y. Raising e to both sides, like we always do, we get v equals y. Perfect. This is a pretty clean example. Not too bad. It's pretty easy to work with. V equals y. So now, working with the rest of the equation, remember, this is equal to 0. So what we're left with is u prime times our v, which was just y, equaling, this is all 0, equaling negative y over 2. Now, remember, the u prime is just du over dy. Now, dividing both sides by y, we get just negative 1/2, right? We divide y by both sides, right? This turns to 1, this also turns to 1. So we're just left with this. Now, separable differential equation, like always, 1/2 dy. So this gives us u equals negative 1/2 y plus c. Very nice, very clean. Let's keep going. For the last step, remember, we have to just plug back in our u and our v. So our x is equal to u, negative 1/2 y plus c, times y. Now, just foiling in, we get negative 1/2 y squared plus c times y. And that's it. We don't have any initial conditions, so this is the final answer. Not too bad. It was a little bit more challenging because of this trick up here, how we applied dx, dy to both sides, but we have to do that because this is not a first order linear differential equation with respect to y. But with x's, it is. So we applied dx, dy to the whole equation, and we were able to recognize it as a linear differential equation, first order, with x's, and we just proceeded with our steps that we already know how to do. So I hope you guys enjoyed this video. I hope it was very helpful for you guys, and if you're taking differential equations this upcoming semester, you're in luck. I'll be posting a lot of videos on it, on every single technique, every single topic in the upcoming future. So yeah, I hope you guys enjoyed. Make sure you leave a comment, like, subscribe, follow me on my social media pages. I'll tag them down below, and have a great rest of your day.